Welcome back to chapter 19. In this chapter, we're going to get that introduction to hypothesis testing, or also called tests of significance. And this chapter, like last chapter, we're going to be looking at proportions. We'll get to sample means later on, but first we're just getting the idea of what is this test of significance. Similar to uh, confidence intervals, they'll be the same. They'll have the same meaning from now until the end. It's just which one we use depends on what kind of information we have. But the tests themselves are basically the same idea. So, hypothesis testing or tests of significance are similar to confidence intervals in that they try to say something about the real world taken from a sample. Now, a confidence interval is trying to estimate that parameter. We were trying to estimate the population proportion based off of our sample. A test of significance or a hypothesis test tests a claim against the population. We think that, or the common knowledge, or historically, the proportion has been this. We think it's more now. So can we gather, or when we gather data, does it support that claim that the proportion is now greater than what it was, or what we thought it was? And so that's the idea behind the testing, as opposed to we're just trying to um, estimate what that proportion is. So hypotheses, they're working models that we adopt temporarily, and we always have two. We have the null hypothesis, which is denoted H naught. That little O down at the bottom is a naught. It just means the original or the initial hypothesis. And that's what we think um, the population is going to be. So if we're looking at dice, we want to see if something's a fair dice. Our H naught for this dice of rolling a 6 would be P equals 1/6. That's how we would write that null hypothesis. H naught, and then a colon, P equals 1/6. It's P, it's the parameter. It's not P hat. We don't need to hypothesize something about our sample. We're going to find out what's about the sample. This is about the population. And it's always equals. The alternative hypothesis is what we're trying to show, or what we think is happening. So it still values the parameter. It's plausible if we reject the null hypothesis. We'll talk a lot about that today. So the example here, if we hope to find evidence that a new medication decreases the percent of infection, H naught would be that P is less than the current percent. I think that dice that we are testing is it's rigged so that 6 is going to come up more often. So my null hypothesis was P equals 1/6. My alternative hypothesis would be P is greater than 1/6. Notice everything is the same except for the signs. We're going to see in just a second, like the null hypothesis is always equal to. The alternative has 3 options. It could be greater than, it could be less than, or it could be not equal to, depending on what we're looking at. This one it's less than, because it's decreasing the percent of the infection. So, I mean, that would be that the new medication is working. And so that's where we'd get the null hypothesis. The number itself is the same. It's 1/6, it's 1/6. I'm sorry, I said that that's where we get the null hypothesis. That's where we get the alternative hypothesis. Um, so the null hypothesis specifies a population model parameter of interest and proposes the value for the parameter. Um, we get that value from a variety of different places. For my dice example, 1, 6. If it's a fair dice, the probability that 6 comes up, it's going to be 1, 6. Sometimes we get the null hypothesis from um, the larger population. Like we might be saying that Stanwood has a um, greater proportion of COVID cases than Washington. So we'd see the um, proportion of all COVID cases in Washington is, I don't know, say 5%. Well, Stanwood would be greater than 5%. So we're testing it against the larger group to see if we were different. And it could be lower too. I mean, it could be one way or the other. Um, so it could be from um, historic data. So in um, um, historically, like in the past 20 years, the House of Representatives has been um, 28% female. Is it significantly more now? So that null hypothesis would be 28 because that's what it was. Are we greater now or less than now? And so, and I don't know if those numbers are right. I just made them up. So don't go fact checking that. Um, and so those are just different places we can get that null hypothesis. Um, so we want to compare the data to what we would expect if it's true. So we find out how many standard deviations away from the proposed value we are. How do we find how many standard deviations we are away? That's just a z-score. You know that thing that we've used, we take it to table A? It's a z-score. We've done this. A significance test, the mechanics behind the significance test is finding a z-score and taking it to table A to find that probability. I mean, I said that we'd be using table A again a lot. That's this. And so then we ask how likely it is to get the results we did if the null hypothesis were true. That's when you take it to table A. The probability that you get from table A is the probability that you have that z-score or more extreme. Higher, lower, whichever way you're going. You might have to subtract 1 minus, just like we always have. But that's the probability of getting the results that we got if the null hypothesis was true. The lower that probability, the more likely the null hypothesis is not true. And so a great analogy to use when thinking about tests of significance is it's like a court case. So we always, well, in theory, we start by assuming innocence, right? You're innocent till proven guilty. And then you have to show that they're guilty beyond a reasonable doubt. And then they're declared guilty. Well, with hypothesis testing, the null hypothesis is true. And then we get the data, we find the p-value, and is it far enough? Is it the p-value is small enough, that probability of getting the results that we got if the null hypothesis is true, is it small enough to say the null hypothesis is guilty, to reject the null hypothesis? Well, that depends. A lot of times the kind of the standard is that 0.05, that 5%. 1 out of 20 times we might get those results by just random variation alone, but that's not very likely. So that's kind of a standard. We do use other ones sometimes, depending. For instance, we might use 1% if um, if it's something that is really going against um, common held beliefs and stuff. But there's no um, like cut and dry line where that is what it has to be. You just get more and more evidence to show that the null hypothesis would be false. So the smaller the p-value, the more evidence you have. Um, and speaking of p-values, so that's the probability that we use. We use the model proposed by our hypothesis to calculate the probability for the events we witnessed. And so that is, we get our data, we find the z-score based on our data, and we're going to see the equations for this. But we go z-score to table A to p-value. So it quantifies exactly how surprised we are to see our results. That's their way of saying it's the probability of getting those results if that null hypothesis is in fact true. So when it's consistent with the null hypothesis, so the p-value is big. It's above 0.05. So it's between 0.05 and 1. We don't accept the null hypothesis. You never accept the null hypothesis. You never say the null hypothesis is true. Because chances are the null hypothesis isn't true, but it might be just a little bit off from what it is. But you never accept the null hypothesis. Just like a court, like a jury never comes back and says the person is innocent. Innocent is not one of the possibilities, one of the possible results of a trial. The results are guilty or not guilty. They never call it innocent. So guilty would be the we reject the null hypothesis. Not guilty, we retain the null hypothesis. Or sometimes, it's not up there, but sometimes it's fail to reject the null hypothesis. That's another way of saying retain. And so it's like you fail to, well, like what we thought was true is true. Like, isn't that a good thing? Like, this isn't about good thing or bad thing. When we're doing a test of significance, the goal basically is to try to get the evidence to reject the null hypothesis. If we thought the null hypothesis, which is like the status quo, was actually like the same, like there was no change, chances are we wouldn't be doing the study or the experiment anyway. So generally speaking, the goal is to reject the null hypothesis. Now, you might not want to, but that would still be the goal when you're doing it. So we can't claim to have proved it, and so there's fail to reject the null hypothesis when the data are consistent with the null hypothesis. And that's just when we'd expect it. So I used the House of Representatives. It was, I can't remember what I said, 23% female. Well, now it's 25% female. We got a couple more women in the House of Representatives. Is that just kind of random variation, or was that like something big? That's what we would use the test to show. Chances are that was just a little bit of random variation, but we don't know. If the p-value is low enough, we reject the null hypothesis, since the probability of getting those results, if it was just like random variation, it was super low, so chances are it wasn't just random variation and our null hypothesis is flawed somehow. And so then we would reject the null hypothesis. Notice this is not about the alternative hypothesis. We do not accept the alternative hypothesis, we reject the null hypothesis. So, here's back to that court case. If the evidence is not strong enough to reject the presumption of innocence, they come back with not guilty. They don't say they're innocent, and all it says is there's not enough evidence to convict or reject innocence. The defendant may be innocent, may not be, just like my the dice that I'm looking at, rolling a 6, it might be 1/6. It might not be. It might have like a slight flaw in it that makes it so it's not exactly 1/6, but it's too close to really make much of a difference. So statistically, we fail to reject the null hypothesis. You never declare it to be true. Never declare it to be true. You can say it has been retained, or we have failed to reject it, but you never say it's true. Remember, statistics is never having to say you're certain. So in a trial, burden of proof is on the prosecution in the hypothesis test. It's on the unusual claim, which is the alternative hypothesis, because the null hypothesis is normal, it's the ordinary, it's the status quo. And so the alternative hypothesis is the unusual one. The three possible alternative hypotheses, as I mentioned, its parameter is less than the hypothesized value, not equal to, or greater than. So that could be P is less than 1/6, P is not equal to 1/6, or P is greater than 1/6. Notice it's not less than or equal to or greater than or equal to. They're simply less than or greater thans, or not equal to. The null hypothesis here would be P is equal to 1/6. This would be my dice example. It's P, not P hat. Later on, when we get significance tests for means, it'll be mu, because it's the parameter, so it's about the population. We don't need to hypothesize about the sample. So our alternative, so when it's a not equal to, it's called a two-sided alternative because it could be either way. So if I was saying that my dice, I think that they're not quite right. I think they're not fair. So they're loaded somehow. And so I just think that probability of rolling a 6 isn't 1/6. I don't know if it's too high or too low. I'm just going to show that it's not 1/6. That would be a not equal to. With that, it's a little bit tough because the p-value, the probability that it is that much or greater, gets split into two. So if I was looking for a 0.5 or 0.05, a 5% one, that means that each side would have to only have 2.5%. Whereas if I was doing a one-sided, that 0.05, so that 5% would all be on one side. So you don't have to be as extreme to show a one-sided test as you do a two-sided test. The one-sided test looks like this. So here, that whole 5% would be there. So the two-sided, you'd have gotten from like there and there. So it would have been, you have to be further away. Generally speaking, we do the one-sided alternative because we know usually whether we're looking for it to be greater than or less than, as opposed to just different. And so it only gets the direction going that way. So if I was looking at my dice and I say, hey, I think that they're loaded, I'm going to get more sixes than just 1/6 at a time. And they are actually loaded, but I get less sixes than 1/6 at a time, it wouldn't give me that information, whereas a two-sided might. Um, so the reasoning of hypothesis tests, there are 4 parts to these, just like there are 4 parts to confidence intervals. They match fairly consistently, and like on the AP test, you can label these parts. You can go like 1, hypotheses, 2, model, which is also called conditions, 3, mechanics, 4, conclusion, and then do each piece separately. I have seen that in anchor papers, and it's a good way of organizing your stuff, making sure that you don't forget to write stuff down, because each of these steps gets you part of your points. So, first, the hypotheses. We have the null hypothesis and the alternative hypothesis. And as um, as I showed before, they would be written basically like null hypothesis, then p equals 0.2, and then alternative hypothesis, p is less than 0.2, or greater than 0.2, or not equal to 0.2. So once we know the null hypothesis, we have exactly 3 options for the alternative. If we know the alternative hypothesis, there's only one option for what that null hypothesis could have been. The model. So we want a hypothesis test. We need to specify the model we'll use to test the null hypothesis. So it requires assumptions and conditions. The model step should end with, because the conditions are satisfied, I can model a sample distribution of the population with a normal model. We'll see what these models are, but they're the same as the confidence interval ones. But sometimes it ends with, because the conditions are not satisfied, I can't proceed with the test. And that happens every once in a while. If you're on, say, the AP test, and it tells you to perform a significance test, you can expect that those conditions should be satisfied. Because if they're not, then you don't even get to the test. That's what they're doing. Sometimes it's a multi-part question where it'll have you check the conditions on part A, and then part B, it'll say something like, assume that the conditions had been met, or assuming that the conditions had been met, or something like that. Then that's a pretty good indicator that, wait a second, something was missing from those conditions. You need to make sure that you double check if you had accepted them. And so the model. So just like with the intervals, each model has a name. You can name the model by the name or by the equation. Sometimes the name is definitely easier because the equations can get kind of ugly with some of this stuff. This is a 1 proportion z test. Last chapter we were looking at 1 proportion z intervals. So the conditions, they're the same as the z intervals. So we test the hypothesis. P equals P naught. Usually you would have a number there like the 0.2. So the statistic, this is the z statistic, the z score. It's the same thing we've done with z equals x bar minus mu over the standard deviation. We have our statistic minus the population parameter. It's what we are assuming the population parameter is. It's what we're testing. It's that null hypothesis divided by the standard deviation of that thing. And the standard deviation, as we saw last chapter, is just the square root of P naught. We're going to use that population parameter. So the P naught Q naught divided by root N. So if we had our H naught was P equal 0.2, HA was P is less than 0.2, and then we run an experiment, or we get a sample where N equals, let's get a sample of 25, and we found that our P hat of those 25 is going to be 0.12. So we could get our z-score. It's going to be 0.12 minus 0.2 over the square root of 0.2 times 0.8 over 25, and that's inside the square root. So 0.2 times 0.8 divided by 25, square root that, gives 0.08, and the 1.2 minus 0.2 is negative 0.08. Over 0.08. Doing some quick maths, this gives me z equals -1. If we take that to table A, which I don't have right off my hand, but we have 68% is going to be inside, which means 32% is outside, which means 16% is lower, so the p-value would equal about 0.16, which is not going to be small enough to be significant. Generally speaking, we use 0.05 as a standard unless we're told something else. On something like the AP test, if they do not give you it's called an alpha level, which is the threshold for your p value. Usually it's like alpha equals 0.05. If they do not give you that, and you have to come up with your own, the p-value is either going to be bigger than anything reasonable or smaller than anything reasonable. So like 0.16, that's a big p-value. So we would fail to reject the null hypothesis in this case. If it was significant, it wouldn't be like 0.45 or something like that. It's usually like 0.001, something in there where it's really small. So that would be how to do the mechanics. Just like the intervals, you can do this in your calculator too. It's just in the same place. So when the conditions are met, the null hypothesis is true. The statistic follows the standard normal model, so we can use that model to obtain a p-value. A sample size of 25 was probably big enough for the central limit theorem to take hold. We have at least 10 successes, 10 failures. I didn't check that. I picked 25 because the square root was nice. The population was close enough to normal, it didn't matter. I just made that part up for the example. The mechanics. That's where the actual calculation of our test statistic comes from. So the different tests do have different formulas and different test statistics. The formulas are all very close to the same, with only a couple exceptions. And the mechanics are handled by a good statistics programmer calculator, but it's a good idea to know the formulas. So in the mechanics phase of this, like we have the first one, we have our hypotheses. We have H naught P equals 0.2, HA P is less than 0.2. So this would be part 1. Part 2, conditions, independent. Check given in problem. We don't have a problem that we're actually working on. A lot of times it's given in the problem though. Independent, normal. Check with a sample size of n equals 25. The CLT says it's normal. We had, I'm going to say n times p naught is greater than 10, which it wasn't, but we're going to pretend. N times 1 minus p naught is greater than 10, and so that checks out. So we can use the normal curve to do our test. 3, the mechanics. Somewhere we need to state the test. We're going to do a 1 proportion z-test. Don't use calculator speak, like the abbreviations that are in the calculator. Don't write those down. Actually use the full words. So 1 proportion z-test. We did that. We got p hat was 0.12, n was 25. So our z value was 1, negative 1, because it was less than the mean. And so the p-value equals, it was 0.16. The p-value is 0.16. That's all you need for the mechanics. You don't need the equations, you don't need the calculations. Like the stuff I did on the last screen, doing it by hand, you don't need that. You're going to use the technology. Like they expect you to use the technology. Unlike the other math AP tests where there's a calculator section and a non-calculator section, the statistics test is calculator on the whole thing. In fact, it says the calculator is required for the entire test. So it's not even really an option. So use it. Don't be afraid to use the technology. It's like, well, but didn't I show my work? Or didn't I need to show my work? This is your work. This is your work. This is your work. It's not the answer. The answer is number 4. So we'd have 1, 2, 3. Ultimate goal calculation to obtain the p-value, which we got. P-value is probability of the observed statistical value, or something more extreme could occur if the null model were correct, and that's just by that random variation. If the p-value is small enough, we reject the null hypothesis. The p-value is not a conditional probability. It's the probability the observed results could have happened if the null hypothesis is true. So the conclusion, part 4. So we had parts 1, 2, 3, part 4. First part of the conclusion is always a statement about the hypothesis. State the decision, either we reject or that we fail to reject the null hypothesis. Need to tie the decision to your p-value, and the p-value should be compared to your significance level, which is alpha, which comes more in the next chapter, but we can use 5% or 0.05. So here, with a p-value of p equals 0.16, we reject or we fail to reject the null hypothesis, or even more wishy-washy, there is good evidence not to reject or or there's good evidence to retain the null hypothesis that P equals 0.2. Now, we don't have context here. We would not want that P equals 0.2 like that. We would want the null hypothesis that 0.2 or 20% of the population is whatever it is that we're talking about. But we have state the p-value. We failed to reject, do not reject, good evidence not to reject, the null hypothesis, and then include context saying what the null hypothesis is, what it means. So how small the p-value has to be to reject the null hypothesis is highly context dependent. We'll talk about that a bit more in a future chapter. But again, conclusion, link it to the p-value of the test, and we could do a confidence interval too. Specifically, if it's a two-sided test and a confidence interval are nearly identical. If you do your confidence interval at the same percent, and the null hypothesis is not in the confidence interval, then that's significant. If it is in the confidence interval, then that's not significant. We would fail to reject. Then the American Statistical Association recently published a statement about p-values, and by recently, this means actually really quite recently. It recommends 6 principles underlying the proper interpretation of p-values. They indicate how incompatible the data are with a specified statistical model. That's a tough sentence to get through. They do not measure the probability that the studied hypothesis is true, or the probability the data were produced by random chance alone. It's not that it's that percent to be true. It's we have that percent chance of getting the data we got if it is true. And scientific conclusions in business or policy decisions should not be based only on whether a p-value passes a specific threshold, because it also looks at what are the costs associated with it, financial and more, and is it different enough even to make a difference? If we had a p-value showing that this like a new curriculum was going to increase test scores by 1%, is it worth spending the money to get the new curriculum to increase by 1%? Like, is 1%, yes, it was statistically significant, but was it like practically significant? So you have to also use your brain. You can't just use the formulas. I know that's rough. Proper inference requires full reporting and transparency. How the data were collected, what the p-value is, what the p-hat is, like all that kind of stuff. P-value or statistical significance does not measure the size of an effect or the importance of a result. It's just what was the chance of getting what we got by chance. And by itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis, because it may or may not be normal, etc., etc. What can go wrong? Oh, all sorts of stuff can go wrong. In fact, there's a whole chapter dedicated to it. The next chapter, actually. So the next chapter is like a continuation of this chapter. But there are a couple things here. Don't base your null hypothesis on what you see in the data. Your null hypothesis and alternative hypothesis should come about before you ever get the data. that happens before that. So you have to think. One of the things that you're going to see here consistently is think. You see, computers and calculators and stuff, they can crunch the numbers for us. They can do the test, they can get the p-value, but they can't decide what it should do. It can't decide if it's appropriate to do it, and it can't decide what that means at the end. Humans have to do that. And so of those 4 parts, the calculator will do part 3. The rest of it requires thinking on your part. Then don't base your alternative hypothesis on the data. Once again, think about the situation. Do we think that it's greater than or less than? Don't make your null hypothesis what you want to show to be true, because you can't prove your null hypothesis. You can reject it or fail to reject it. Base your null hypothesis on not what you think is true, but what the general thing, or what was true, or what people think is true that you're trying to disprove. Don't forget to check the conditions. How many people forgot to check conditions when we were doing a practice confidence interval? We're going to keep doing this, and I keep repeating stuff even inside these videos. They get long because I repeat the same stuff several times, because that stuff that I keep repeating over and over and over again is important and generally misused or mistaken, or something in that area. Don't accept the null hypothesis. You can fail to reject it. You can retain it, but you do not accept it. And I don't think the bigger sample would be more likely to lead to a rejection as well. And don't just keep taking samples too. That's something that people do too much in the world that's wrong. They'll do a sample. It's like, oh, I didn't get the data I wanted. We'll do another sample, do another one, do another one. I mean, if you're at a 95% level or a 5% significance level, if you do 20, chances are one of those 20 is going to give you the data that you're looking for. That's bad statistics. You do one sample. Then don't say you prove the alternative hypothesis. You know, if we had a p-value, like we had a p-value of 0.16, let's say our p-value is 0.02. Hey, with a p-value of 0.02, there's good evidence to reject the null hypothesis and say that the actual population proportion was less than 20%, whatever that proportion was of. If you fail to reject the null hypothesis, don't think the bigger sample, again, a bigger sample does not fix everything. What have we learned? Learned to use what we see in a random sample to test a hypothesis about the world. They're very similar to confidence intervals, but again, confidence intervals are estimating the parameter. Hypotheses, or the tests, are testing an idea or a hypothesis about the parameter. Yep. We've learned that it requires 4 important steps. We have to write the hypotheses. Step 1. Step 2, determine what test to use, and then check the conditions. Step 3, complete the mechanics. And again, that completing the mechanics, z equals p equals. That's all that takes. As long as you say what test you're using up in part 2. And then step 4, link the p-value to the decision and state the conclusion in the proper context. And so that is the answer. 1, 2, and 3 are the work to get the answer. It looks different than other math classes, but that's what it is. Um, so we can get hypotheses, the null and the alternative, write them the appropriate way, H naught, then the colon, P equals, HA, P is greater than, less than, or not equal to. Learn to confirm that we can use a normal model. It's the same thing we've been doing for the past couple chapters. Check the independence, the randomization, the 10%, and success failure. If all of them check out, you have a normal model. You can do a 1 proportion z-test. The mechanics, these are those equations again. It's really just the z-score. And then the p-value, again, is the probability of observing an outcome at least as extreme as ours if the null hypothesis is actually true. Learn to state appropriate conclusions. If the p-value is large, we fail to reject the null hypothesis that the population proportion is whatever it is. If it's very small, it's very unlikely that we would get that by chance, and so we reject the null hypothesis, saying that the population is less than that. So if we had their null hypothesis was 2 or 0.2, and the alternative hypothesis was it was less than 0.2. If we had a small p-value, we would reject the null hypothesis and say that, hey, our population proportion is less than 0.2. That does not tell us what it is. It just tells us it's less than 0.2. It could be 0.19. It could be 0.1. We don't know. We have nothing to say that for that, at least at this point in time. Then some AP tips. Check your conditions. Always. Write your conclusion carefully. Make sure your the p-value linkage, so it's less than or greater than your significance level. Sometimes you can do it without actually tying it to the significance level, by saying that, with a p-value of 0.02, that's sufficiently small, so there's strong evidence to reject the null hypothesis. With a large p-value of 0.16, there's not evidence to reject the null hypothesis. Like, you can get away with not linking it to an alpha level. If you do link it to an alpha level, though, you do have to make sure that you state that before. And we'll talk more about that in the next chapter. And then accepting H naught will always cost you points. Never accept the null hypothesis. So, anyway, this was the introduction on tests, and then looking at those one proportion z-tests. We'll have more tests coming up, but they're all basically the same, and the meaning is the same. The steps are the same. The difference is which conditions are there, and the equations will be a little bit different. So, with that, I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.